Okay, my name's Carl Schmidt. I'm a researcher at a laboratory called LATMOS in Paris, France, and I study planetary atmospheres there. So here's some more data from stereo, which is self-subtracted. So it's a running average where you subtract one frame from the next and keep going in time. And this is the data that people were sifting through to look for new comets. The comet that I'm going to talk about here is this one coming in the lower left. It's called Comet ISON. And that was the brightest comet in the last few years, which has been well observed by ground-based telescopes from the Earth. And we have really learned a lot about the atmosphere through this comet in particular for that reason, because it's bright. But the comet plunged into the sun and never returned. A lot of comets get brighter after they pass nearest to the sun and release all of that material that then glows in sunlight. But Comet ISON came so close to the sun that it just fell in. It just blew up on its closest approach. And a lot of the people who had studies of this comet plans, with the Hubble Space Telescope and these other facilities, couldn't take those measurements because there was no comet to look at. So Comet ISON was easily observed by narrowband imaging like we're using for these observations of Io and Mercury. And the comet was actively disintegrating. It was falling apart. That disintegrating comet changed the brightness of the atmosphere by about a factor of 4 overnight in some of these observations. That's a really dramatic, sudden change in brightness. Things like that are interesting for learning about how comets disintegrate and how they break apart and form different structures and the chemistry that's going on. So the on bands and off bands were again subtracted, and we can disentangle all of that scattered light to just isolate one species, which sodium is the bright one here. That data can be compared with a model in order to study what is the overall source rate of sodium in this comet's atmosphere. So as it was disintegrating, that source rate changes. And we can learn from a model that not only is sodium coming from near the nucleus, near the actual solid comet itself, but it's also coming from an extended dusty tail behind the comet. So your original source of an atmosphere isn't just the surface, it's a dusty atmosphere behind the surface. And you see a distribution in the tail which is more flat as a function of distance than you would expect for just an atmosphere which is getting blown away from sunlight. So you know that there's an additional source behind the comet in order to make that flat distribution. When the comet got a lot brighter the following day, we don't observe this distant dusty tail source getting brighter, but we do observe the comet atmosphere near the comet surface getting dramatically brighter very fast. And so the dusty source, in fact, takes weeks to change because the dust needs to propagate all the way down the tail, whereas the source, which is near the comet's solid nucleus surface itself, can change very quickly because the gas is coming off directly there. So within just a few hours, we can see a pretty dramatic change, and we can constrain those timescales from this type of modeling. With the integral field spectroscopy technique, the spectrum for every pixel in a comet gets very interesting. And this is an area of astronomy that's well suited for small telescopes that isn't really being well explored yet. So for each of these spectra, we get some bright emission from the nucleus of the comet, and then some spectra in the tail. We see different emission lines for different species there. Once we line up all of those spectra, these bright lines down at the bottom are the well-known sodium transitions that we've been talking about. But those lines up on top that are seen flat across corresponds to water ions. If we look at the spectrum of this comet, it's pretty messy. There's almost 500 different transitions from diatomic carbon and amine, NH2, at many wavelengths over just a small bandpass. So it's a very messy spectrum because of all of the molecules in the comet's atmosphere. Those molecules have so many transitions in them that the spectrum just has continuum lines because of them. But we also have lines coming from ionized water, which was originally ice in the comet, and from sodium. There is a number of papers which describe carbon monoxide as being visible in visible wavelengths in comets. But those are actively debated, whether or not we're seeing those transitions in fact. And they're interesting transitions of carbon monoxide because the only way to cause those electron de-excitations are if carbon monoxide was left in an excited state from a parent carbon dioxide molecule. So if we can detect those lines in the visible, we would have a brand new way of knowing how much carbon dioxide was in comets that we can use small telescopes for. And it would be very exciting. Taking a spectrum like this, you can isolate just a certain wavelength at each one of these species and look at what the spatial distribution at that wavelength is, and even co-add several bright wavelengths for these molecules in order to back out the spatial distribution of what the comet looked like. Those spatial distributions look something like this, where the sodium forms a tail structure due to radiation pressure. The water ions form their own tail structure, which is due to their pickup in the solar wind and the sun's magnetic fields that's moving through interplanetary space. And the neutral heavy things, like diatomic carbon, like amine, they're more or less spherically symmetric around the comet's surface. With the continuum, emission on a comet which is not at a particular transition of an atom or a molecule, we can monitor the dust, which is just scattered sunlight reflected off of cometary dust. So using this technique of integral field spectroscopy, you can get an image of the comet at all of these different wavelengths, which correspond to ions, or one type of gas which is atomic, one type of gas which is molecular, or dust. And you can really disentangle the different processes that are happening inside a comet's atmosphere using integral field spectroscopy. And it works with small telescopes if a comet is sufficiently bright. So in this plot here, we're giving a radial fall off of what is the emission as a function of distance from the comet. And these are distances of tens of thousands of kilometers that we're talking about. Dust, if you just spread it out and don't change the total amount of dust, if you look with distance from the comet, that's going to give you just a 1 over distance fall off. in terms of the scattered sunlight that comes from dust. So 1 over r is a flat line that's given in black here. Anything that is an ion or a neutral will have a faster fall off than that 1 over r because it's being accelerated and it's being photoionized. So for photoionization, we can use a simple model. How does the photoionization make that fall off change? And then how many different molecules go into the species that we're observing? So NH2, amine in comets, doesn't just come off the surface as amine. It probably comes from NH3. And NH3 has its specific photoionization rate, which has a curve away from the sun. And then NH2 has a different curve because it gets photoionized differently. So we combine those two together into a model of how should the brightness change as a function of radius for what the different parent species are, to learn, well, does diatomic carbon come from C3, 3 carbon atoms bonded together? And does amine come from NH2 or NH3? We can learn about the parent molecules that go into these different transitions of molecules that we're observing. So all of these distributions from NH2, from C2, they show more emission farther from the comet than the models predict. And the only real way to do that is if we're changing the source rate of how much material the comet is leaking out. So the overall outgassing rate of the comet must have changed on a short time scale in order to observe this. That exciting carbon monoxide distribution that a number of people have proposed that you see in the visible shows a very different curve where it should be flat, but it falls off a little bit faster and it's closer to the other ones. If this was in fact light coming from carbon monoxide, it should be well above the purple dotted line. It's not, and so we know that those papers are actually incorrect, that we can't detect carbon monoxide via those lines, and if we did, we would see it in a shell spectroscopy, where we just have a point source. Some lines would have a certain ratio of brightness. We didn't see that either. So there's a lot to be learned with this technique for all of the species in comets, and to just go through some summary of what we learned for Io and Mercury. Io's volcanism can be monitored with small telescopes directly, but only in eclipse where the bright sunlight is blocked by Jupiter's shadow, and you can only observe that bright emission from the volcanoes themselves, not from reflected sunlight. The sodium nebula is a proxy for the overall volcanic emission, and that sodium is uniquely bright, and you can study it with small telescopes. Small telescopes can teach you about Mercury's atmosphere, how that atmosphere is escaping as Mercury orbits the sun, and how its atmosphere is lost into space. And it can even teach you about Mercury's magnetosphere, because Mercury's magnetosphere is offset relative to the center of the planet. That induces an asymmetry, and that asymmetry gets imprinted in the atmosphere. We know that that atmosphere isn't created the way that we thought it was by solar wind ions coming down to the surface and liberating an atmosphere from the rock directly. It's certainly influenced by that, but it's not energetic enough for that to be the dominant source. It needs to be something else. And for right now, the best term that we have is ion-enhanced photon-stimulated desorption. And that's a mouthful. We need a better word for how we're making the atmosphere of this planet. But that's the actual process that the data and the models seem to have converged on. And for comets, we can see from the water outgassing rates and the sodium outgassing rates that this particular comet, Comet Ison, had a very, very low relative abundance of one species to another, of sodium to oxygen. It's the lowest that's been observed in any comet ever, and it's kind of unusual for an Oort cloud comet, which should have a relative abundance for different atoms that matches the sun, that matches carbonaceous chondrites, which is the primordial material that formed the solar system. That has a predicted ratio of one atom to another, and when we don't see a comet match that, it teaches us something new and raises new questions. Because the distribution of water ions and sodium is very different from one another, we know that sodium isn't formed from sodium chloride, which is ionized, NaCl+, like it was for this distant sodium cloud around Jupiter. Were that the case, the two tails of the comet would resemble one another in their structure, and they're distinctly different. There's no way to get one narrower than another if both had trajectories that correspond to ions trapped in a magnetic field. The overall gas production was quite variable, and we can figure out what the collision cross-section is of how the outgassing water is pushing on the sodium and creating the width of that tail that we're observing. So we're actually learning about atom-to-molecule collision cross-sections through this kind of study. And it's important to consider this sort of opportunity that we have if we apply unique instrumentation to study just one specific effect, and even to monitor specific effects in the case of Io and Mercury as a function of their season, as a function of volcanism. These underutilized resources can really provide the science community, and it comes at a very low cost for a lot of space programs and university budgets. It's within reach to do science with small telescopes, whereas sending a spacecraft or a satellite into space is a much larger project. And finding the balance in order to maximize the science productivity between those two requires not always just looking at the largest, biggest, newest instrument, but also paying attention to what you can do with underutilized resources. If you think about just a niche application for what we can study with this small telescope at one location or another in our backyard.